What is the Pythagorean theorem? I would describe the Pythagorean theorem as a relation between the three sides of a right triangle. Before we move any further, though, let's be clear what a right triangle is. A right triangle is any triangle that has a right angle or a 90-degree angle. So we're not talking about isosceles or equilateral or scaling triangles. All right, let me start with the question. Let's say I plated each of these squares in gold, and I gave you the choice. You can either have the large gold-plated square, or you can have both of the two smaller gold-plated squares. Which would you choose? Whichever your choice, it was a good choice. And here's why. This large square, I have a 5 by 5 square, and that gives an area of 25. This medium square, I have a 4 by 4 for an area of 16 square units. And the small, a 3 by 3 for an area of 9 square units. When I combine the areas of those two smaller squares, I have 9 plus 16 for an area of 25. And hey, that matches the area of that large square. That's pretty cool. However, is this true for any right triangle, or was I just being clever in choosing a 3 by 4 by 5 triangle? So the question we're getting at is, well, what if I didn't know the 3 and the 4 and the 5? And let's say this was A by A, and this was B by B, and this was C by C. Would it still be true that the area A squared of that small one plus the medium one, the area of the medium one, is equal to the area of the large one? So it turns out it's always true. And there's literally hundreds of proofs, maybe more proofs for the Pythagorean theorem than any other theorem in math. So we're not going to get into any of the formal proofs, but I have an interactive tool here to see many different examples of right triangles. So here's that 3 by 4 by 5. Now this, I can change the size of the triangles. And so what we'll notice is, regardless of which size I choose, those two small ones will always add to the large one. So here we have 22.3 for the medium, 1.4 for the small. Add those together and we get 23.7, matching that large square there. So it's true, a squared plus b squared does indeed equal c squared. All right. So that's a pretty cool thing, but let's actually talk about some usage. So there's evidence of it being used for thousands of years. One really cool usage that I like, I believe the Egyptians may have used it, not direct evidence, but there's evidence of Pythagorean theorem or Pythagorean triples, these integers for each side, like a 3, 4, 5 triangle, being used in Egypt, India, Mesopotamia by the Babylonians, of course Greece, Pythagoras was from Greece, and China as well. But here's a cool potential usage we had seen thousands of years ago, and that is, if let's say I had a rope, and then these two ends, I tied those two ends together. Now, in this rope, I also put in 12 equally spaced knots. Now, here's what's pretty cool, is that if I follow that 3, 4, 5 triangle, now is the point of using 12, 3 plus 4 plus 5 equals 12. If I pull at that 3, 4, and 5 spot on those knots on this rope, it's going to snap into a 3, 4, 5 triangle, which is a right triangle. So pull out on this one and then count out 3, and pull out on that third knot, count out 4, pull out on that knot, and then lastly count out to the 5th knot. 3, 4. That brings us back to that 5th knot. So what I end up with is, let's see, we got that green knot, and then the yellow knot, and then I wanted that blue. And then our blue knot. This is going to snap into a right triangle that's 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, with the 3 by 4 by 5 triangle. All right. So there's one cool usage. You can make right angles. Let's do its most common purpose, and that's finding the missing side of a right triangle. So let's say we had a right triangle here. This was 41 feet by 50 feet. And this one we don't know, so I'll just call it A. Now I could call it B, A or B, but when I have this equation for Pythagorean theorem, it's customary to just reserve C as the long side, and that long side's always the one that's sitting alone on one side of the equal sign. So C is that long side, or what we call the hypotenuse. The easiest way to find the hypotenuse is it's the side opposite the right angle, or the 90-degree angle. And so that's the hypotenuse. Hypotenuse. All right. So, and then the two short sides, these are called the legs. So those are the legs of the triangle. And then the long side is that hypotenuse. All right, so let's find what A is. So I could come back to our Pythagorean theorem equation here, formula, and I don't know A, so I'll just keep it as A. Plus B, I know B, 41 squared, and C, I know C is 50, so 50 squared. All right, so a little algebra here, move that 41 squared over, and I'm left with A squared equals 50 squared minus 41 squared. And take the square root of both sides. And I am left with A equals the square root of 50 squared minus 41 squared, which comes out to approximately, just punch that out in a calculator, 28.6. And that would be feet, in the context of our original problem being in feet. All right, so there's a usage. Now, something interesting about Pythagorean theorem is we're almost always talking about the squares coming off of the sides of the triangle. However, this can be generalized. It works for literally any similar shape that we want to form off of the sides of the triangle. So here we've got a semicircle, equilateral triangle, square, regular pentagon, hexagon, septagon, octagon, right? Any shape that is similar on those three we can use. And so here, no matter what size right triangle I choose, what right triangle I want to make, these three, the two areas of the smaller shape will be equivalent to the area of that large shape. So there it is, the Pythagorean theorem.